Hello students, welcome to this online course of engineering mechanics. So in the previous lecture we have seen about the virtual work. Now let us see what is work, energy and power. This basically you have been covered in the mechanics part, but just to brush up your concepts, let us see what are these terms and how we are going to apply these in our engineering. So let us start with work. So what is work? Whenever a force acts on a body and the body undergoes some displacement, then work is said to be done. So for work to be done, the displacement and force should either of one should not be absent. When both are simultaneously present, then only work will be done. If force is there and the displacement is zero, then the work done is said to be zero. If displacement is happening automatically without any force, then also the work done is said to be zero. So the displacement should be there, that too along the direction of the force. If the displacement is in perpendicular direction to the force, then also the work done will be zero. Even the displacement and force both are present simultaneously. Why? Because the work done is the dot product. Here you can see this is the dot product, F dot F, and this is dot ds. Both are vectors, but the resultant quantity, which is work, is a scalar quantity. This we have seen in the previous lecture, why this work is said to be scalar quantity, because it is independent of the direction. So U is work done, F is the applied force, S is the displacement, and theta is the angle between S and F. So it is nothing like only force can do work. If moment is there and some kind of rotation is happening due to that moment, then also work is said to be done. Okay, and it is like sorry for this, and this work will be m dot d theta. D theta is the rotation due to the moment, applied moment m, and the SI unit of the work is joule, that is kilonewton meter or newton meter. Sorry, here it is not second, here it is meter. Joule is here, meter is there. Okay, so how we are going to define 1 joule? 1 joule is a work done by 1 newton force causing 1 unit displacement. Okay, the dimension of the work of a force and the moment of a force both are same, but they are completely different quantities. Okay, moment and work are having the unit of kilonewton meter or newton meter. They are having the same dimensions, force and multiplied by displacement, but they are completely different physical quantities. Okay, now let us see what is power. Power is the rate of doing of work. If we are calculating the work done in for a particular amount of time, for a particular interval of time, then that rate is the power. The rate of work done is power in simple words. It is thus the measure of performance of engine. For example, an engine doing a certain amount of work in 1 second will be twice as powerful as the engine doing the same amount of work in 2 seconds. Okay, if particular engine is doing 2 times and taking the same work in half time, then it is more efficient and it is doing double, it is having a double power. Okay, so what is the SI unit? SI unit is energy work done by time, that will be newton per joule per second or watt. So bigger units are kilowatt and megawatt. Kilowatt means 1000 watt and megawatt is 10 raised to power 6 watt. So P is dW by upon dt, and W is what? F dot dr. So we can also say it is force multiplied by velocity. Okay, so now let us move to energy. So this is very basic unit, only just to brush up your concepts. it is being taught to you. So what is energy? Energy may be defined as the capacity to the work. How much capable are you doing for some kind of work? That measure is the energy. If you are able to do more work, then you are having more energy, and if you are able to do less work, then you are having a less energy. So it exists in many forms. Energy can be of many forms, like mechanical energy, electrical energy, chemical, heat, light, etc. SI unit is same as that of work. So work and energy are having same SI units or same dimensions. Though there are many types of mechanical energies, yet the following two types are important: potential energy and kinetic energy. So these two type of mechanical energies are important for engineering point of view. Now before moving to the numericals, let us see what is the work energy theorem. This also you have learned in your mechanics classes in class 11th, but still let us just try to see what is this statement is stating: that the work done by the sum of all forces acting on a particle equals the change in the kinetic energy of the particle. So if we are able to calculate the change in kinetic energy from one position to another position, or one particular time to another particular time, then that will be equal to the sum of all the work done by all the forces. Clear? So this is half mv2 square minus half mv1 square. So this is work energy theorem. Now what is conservation of energy? This you are studying from class 6th, I guess. The energy can neither be created nor be destroyed, though it can be transformed from one form into any of the other form in which the energy can be existing. So you might have seen that, like you might have seen heard about the turbines by which we are getting the power. What is happening there? So we are using the water energy. So water is moving the turbine, and that turbine receiving the mechanical energy from water. It is being that mechanical energy is being converted to the electrical energy. So this type of transformations are possible, but we cannot generate the energy. It can only be transformed. Now let us see few examples, very simple examples. So a horse pulling a cart exerts a steady horizontal pull of 300 Newton and walks at the rate of 4.5 km per hour. How much work is done by the horse in 5 minutes? So we are having speed, we are having time. We will calculate the displacement, and displacement multiplied by the force will be your work done. So this you will be getting 112.5 kilonewton meter. Now the second problem is: a spring is stretched by 50 mm by the application of force. Find the work done if the force required to stretch 1 mm of the spring is 10 Newton. So stiffness is given, that is 10 by 1 mm, it is stiffness, and the energy work done of a spring is half kx square. You can see here. So this is the work done, half kx square. K is stiffness, x is displacement. So this is also given, this is also given. Just put the values, you will get 12.5 joule. So let us see the next problem. Find the power of an engine which can do work of 1200 joule in 8 seconds. So it is the simplest problem. Power is work done per unit time. So 1200 divided by 8. So it is coming out to be 150 joule per second, or 150 watt. Next, a motorboat is moving with a steady speed of 10 meter per second. If the water resistance to the motion of the boat is 600 Newton, determine the power of the boat engine. So power is force into velocity, as we have seen. So both are given. 600 into 10 will be 6000 watt or 6 kilowatt, because 1 kilowatt is how much? 1000 watt. So just divided by 1000. Next question: a locomotive draws a train of mass 400 tons. So train is being drawn by the locomotive and mass is 400 ton. 1 ton is 1000 kg, including its own mass on a level ground with a uniform acceleration until it acquires a velocity of 54 kmph in 5 minutes. Okay, if the frictional resistance is 40 newton per ton of mass and the air resistance varies with the square of the velocity, find the power of the engine. Take air resistance as 500 newton at 18 kmph. Clear? So this is the question. Try to read the problem first, try to solve the problem by yourself, then come to the solution and try to match and check where you are doing the mistakes. So mass is given, velocity acquired is 54 kmph, so we have converted it into meter per second. Time is 5 minutes, that is 300 seconds. 5 into 60. Frictional resistance is 40 newton per ton and the mass is 400 ton. So just multiply 40 by 400, you will get 16,000 newton or 16 kilonewton. Now from the Newton's first law, we know that V is equal to A plus U plus AT. So this formula you have seen in your 11th class itself. So from here we will calculate the acceleration. We are having mass, then we can get the force. Now, as stated in the question itself, that as the air resistance varies with the square of the velocity. So for 18 kmph it is given as how much? 500. So for 54 it will be 54 by 18 square into 500. Why square? Because it is given in the question itself. So it is coming out to be 4500 newton or 4.5 kilonewton. Now the total resistance is how much? 16 by the frictional, 1220 by the speed, and 4.5 by the wind resistance. Power is how much? Force into velocity. Force is 40.5 kilonewton into 15. So it is coming out to be 607.5 kilowatt. If you are having any doubt, just feel free to ask. Don't hesitate. All the queries will be solved. Now let us check this problem. A wagon of mass 50 tons starts from rest and travels 30 meter down a 1% grade. 1% means 0.001 and strike a post with bumper spring as shown. So you can see here, so this is wagon, it is moving like this and it is hitting here. If the rolling resistance of the track is 50 newton per ton, find the velocity with which the wagon strikes the post. Also find the amount by which the spring will be compressed. If the bumper spring compressed 1 mm per 20 kilo Newton force. Stiffness is given. Now let us start the problem. What is given? Mass is 50 ton. Initial velocity is 0 because it is starting from the rest. Gradient is 0.0, that is sin theta or tan theta, one and the same thing. Track resistance is given as 50. How much? 50 Newton per ton, and the mass is 50 ton. So 50 into 50, it will be 2.5 kilonewton. Spring constant, that is K, 1 mm per 20 kilonewton, that is 0.05 mm per kilonewton. So initial velocity is given. Okay, now velocity V we have to calculate. Distance is given as 30. If we are able to calculate the acceleration, then we will be able to calculate the final velocity from this formula. V square is equal to U square plus 2S. This is 0. S is given. A we have to calculate, then we will get the V. Now the net force along the motion will be how much? Gravitational pull minus tractive resistance, that is friction. It will be acting opposite to the motion. So 4.9 is how mg sin theta downwards minus 2.5 from the tractive resistance. So the net force is 2.4, and this net force is equal to mass into acceleration. Because of this force only motion is possible. So A is 2.5 upon 15, that is 0.048 meter per second. So this is your acceleration. Put it here and you will get velocity as 1.7 meter per second. So this was the first part. Now second part is we have to calculate the compression. So let x be the amount by which the spring will be compressed. So kinetic energy of the wagon is how much? Half mv square. And we have calculated, m is given. So it is coming out to be 72,250 kilonewton mm. Now the compressive force will be how much? X upon k. K is 0.05. X is in mm and this is also mm per kilonewton. So compressive force is 20x kilonewton. Work done in compressing the spring will be how much? Half load into distance. Half into 20x is the load, compressive force, and x is the compression. So it is coming out to be 10x square. Now change in kinetic energy is equal to total work done. So we have to equate both values. So 10x square will be equal to 72,250. From here you will get x is equal to 85 mm. So try to solve more problems, and this much is enough. But if you want to learn more new concepts, try to solve more problems. If you are facing any problem, try to ask, don't hesitate. Okay, if you are hesitating here, it will become your habit, and finally you will not get to learn the new things. So this is all for today. Thank you.